Welcome to the course on An Introduction to Information Theory. I am Adrish Banerjee, and today we are going to talk about variable to block length coding. So there are many applications where the output block size is fixed. And how do we get source compression in those cases? So there we like to map large input blocks to fixed length output blocks. And we get compression by varying the input block size depending on the probability of occurrence of those bits. So in this lecture we are going to talk about how to do variable to block length coding. We'll talk about a method to parse input sequence into blocks of variable length, and in particular we'll talk about one particular case where we know how to do this variable length coding optimally. So today's topic of discussion is on variable to block length coding. We'll describe what we mean by a source parser known as proper message set, and then we will talk about how do we assign probabilities to a rooted tree. This we will use to obtain bounds on expected code word length. We will also talk about how to do prefix free coding of a proper message set. Subsequently, we will define what is an optimal proper message set, which is known as tungsten message set, and we will talk about optimal variable to block length coding when the source parser is parsed according to a proper message set, and that's known as tungsten coding. And finally we'll give basically bounds on expected code word lengths. So let us start this discussion. So the problem that we are looking at is as follows. So we have a discrete memoryless source which we want to which is emitting some bits, and we want to design a source parser of variable length. So what this source parser does is it takes these bits and it converts them into blocks of data where the block length is variable. So this y is a random variable, and after you parse the source into input into blocks, what this block encoder will do is it will map these blocks of data into code words of fixed length n. So n here is the output code word length, that's fixed. Input block size y is variable. So our objective is to design a source parser which will do this variable length parsing of the input bit stream, and our input block size y is a random variable. Ideally we like y to be large and large because n is fixed, and average number of bits for the DRE code word per source letter is given by n by expected value of y, because n is the output code word length and expected value of y is the expected input code word length to this block encoder. So a measure of goodness of this compression is this ratio n by expected value of y. So clearly if you want to get good compression, we would like your expected value of y to be as large as possible for a given n. So our objective here in designing this variable to block length code is to parse the source in such a way such that expected value of y is maximized. Now how do we do this source parsing? So that brings us to this concept of proper message set and improper message set. So look at first this example. Let's say I have a source that emits three bits. It's a ternary source which emits A, B, and C. And let us look at this particular message set. So what it does it, so it passes the bits. If you get an A, that's one parsing of the message. If you get a B, that's the message boundary. If you get a C, then you look at the next bit, CA, CB, or CC. Let's look at some sequence of this thing. Let's say A, B, A, C, C, B. Okay. Now, note here that if I use this source parser, which I am calling as proper message set, so how will I parse this input sequence? So there is a, for A, that's 1, B, A. If I get a C, I look at the next bit, that's CC. So this is how I am partitioning it into different blocks, right? So if I get an, so A is one boundary of the parsing, B, so I am parsing the sequence into A, B, CA, CB, and CC. Note here that you give me any data stream, I should be able to parse my message stream into this A, B, CA, CB, CC. So what is special here? So you can see here, if I am drawing this message set in form of a tree, you note that all the leaves of this tree are being used for parsing my message sequence. So a proper message set of a query source is a set of messages that form complete set of leaves for a rooted query tree. So if you have a query tree, I am not saying that this tree has to be full query tree. You need not like extend all the nodes up to the full depth, but you should always have a message correspondence from the root to each of the leaves. So if I get a sequence which has A, that's my block, B, that's my block. If I get a C, I look at the next bit, and depending on my next bit is, that's how I parse my sequence. So this is my set of sequence that's coming in, and that's how it is getting parsed. Now look at this particular example, which I am calling a improper message set. Now if you look here, if I get a A, I am parsing the sequence. If I get a B, I am parsing a sequence. If I get a C, I look at what's my next bit is. So I parse it at CA, CB. But there is nothing for CC. So if I get a CC in my input sequence, this particular source parser, which I am calling as improper message set, cannot parse my input into blocks of data. Again, recall, basically our objective is to design this. We have a bit of bit stream coming in. We want to divide that bit streams into blocks of data. Now how do I do that? How do I parse the source into blocks of data? And of course, remember that my objective is to maximize expected value of y, because my code word length n is fixed. So I get compression by mapping large blocks of input data to this code word of length n. So I would like to maximize my expected value of y, and so my source parser I have to design which will parse this input streams into blocks of data, and then I will map these variable length blocks into code word. So what this proper message set we just showed you with an example was, if I choose a proper message set like this, I am able to parse my any ternary input set into blocks of data. Here the block is A, B, CA, CB and CC. Now look at this particular example. The problem with this particular example is, since we are not using this leaf, so whenever our input sequence CC comes, we are not able to parse it into a block of data. So if you look here, if I get an A, my input stream is sparse. If I get a B, input stream is sparse. I again get an A, input stream is sparse. A. Now if I get a C, so note that if I get a C, I need to look at the next bit. The next bit is CC, but CC is not used. So if I give this particular input stream to my message source parser, which is parsing my sequence like this, I cannot parse sequences which are of type CC. So this is an example of a improper message set. So in a proper message set, we are using all the leaves of a k-array rooted tree, whereas in an improper message set, we are not using some of the messages. So clearly we cannot parse a source using an improper message set. Now I want you to look at another type of improper message set, which we can call also as, sometimes known as quasi proper message set. So quasi proper message set or improper message set. So note here also we are not using these two leaves of the k-array rooted tree, but this can be used for message parsing. How? Let's look at it. So if I get an A, that's where my one boundary is. If I get a B, that's one message boundary. If I get a C, note, I will look at what comes after C. If A comes, I will use CA, that's my message boundary. If B or C comes, I will just use C. So if you look at this particular example, if I get an A and I use this message set, this is my message boundary. If I get a B, this is my message boundary. If I get a C, this is my message boundary. If I get an A, that's my message boundary. That's how the source is getting parsed. If I get a C, I will look at the next bit. The next bit is C. So in that case then I will parse it at C and then C and B. Now if this would have been C A, then what I would have done was I would have parsed it. If this would have been CA, then my message boundary would have been CA. So what is the difference between this and this? What's the difference between this and this? In this particular example, note, I am able to parse all possible input sequence. So if I get C, what I am doing is I am waiting and seeing what is the next bit. If the next bit is A, I mark my message boundary or at CA. But if the next bit is which is following C is either B or C, then I will parse my message. My message boundary is just C. Now the problem here is, in this particular case is, if I get a C, then of course if I get a C and A, it is similar to I am doing here. But if I get a C and B, then my message boundary is CB. But if I get a C and C, since this leaf is not been used, it cannot parse any sequence which is of the form CC. Right? Now let's compare this with this. What is the difference between this proper message set and this quasi proper message set? Now both proper message set and quasi proper message set both can parse all possible input sequence. We have seen that you give a ternary input sequence, it can parse ternary input sequence. What is the difference? The difference is, in case of a proper message set, when a bits are coming, I know exactly where the boundaries are. For example, when A is coming, I know that's my input block length boundary. If a B comes, I know that's the input block length boundary. If a C comes, I look at the next bit and I know that's my message input message boundary, CA, CB, CC. Now what's happening here? If A and B are coming, I know that's my message boundary, but if a C comes, I do not know instantaneously whether that's my message boundary or I should look at next bit. That depends on, so once I get a C, I need to look at the next bit to decide whether my message boundary is at CA or I should just have message boundary at C. So I cannot instantaneously tell how to parse the source message. I need to look at the next bit and then decide where my input bit stream should be parsed. So that's the difference between a proper message set and a quasi-proper message set. Both can parse the input sequence. In one case, I instantaneously, when the bits come, I know where the message boundary is. In the second case, I will have to look into further bits in the future before I decide where the message boundaries are. Okay, so I have given example of various ways in which you can parse the input message sequence. Clearly, if I use a proper message set, I can parse all input sequence and I can instantaneously parse the bits. If I use a quasi-proper message set, I can parse all input sequence, but I may not be able to do it instantaneous. I may have to look at some bits in future and then decide my message boundary. Whereas if you are using an improper message set, then you cannot parse all possible input sequence. So we cannot use this improper message set for source parsing. Now in case of a proper message set, we know, remember our objective is to maximize expected value of input code word length. We want to maximize expected value of y. In case of a proper message set, we know a method to do that. We know a method to find optimal code which will maximize expected value of y. Whereas for a quasi-proper message set, we do not know an algorithm to find a way or find a code which will maximize expected value of y. So in this lecture, we are going to concentrate only on proper message set. How do we design a source parser using proper message set such that our expected value of y is maximized. So now we first are going to show you how to assign probabilities to k-array rooted tree corresponding to a proper message set. This got clipped, message set. So how do we assign probabilities to a k-array rooted tree? You have seen in the previous slide, we have represented this proper message set using a k-array rooted tree. Now how do we assign probabilities to these leaves? That's what we are going to talk about next. So let us take an example again of a source which emits ternary sequences A, B and C, and let us say probability of occurrence of A is 0.1, probability of occurrence of B is 0.3, probability of occurrence of C is 0.6. So first thing, the root is assigned a probability of 1. So in this case, this is my root, so this has probability 1. Each subsequent vertex is assigned a probability which is equal to probability of the node from which it stems multiplied by the probability of the letter emitted by the discrete memoryless source on the branch connecting that node to the vertex. So then according to this, what should be the probability of this? What should be the probability of this vertex? This probability would be probability of this node multiplied by probability of occurrence of this letter A. So this is 1 into probability of A was 0.1, so this is 0.1. Similarly, what is this probability of this vertex? Probability of this node is 0.6 and probability of occurrence of A is 0.1. So, this is 0.6 into 0.1, that is 0.06. So, we can find probability of any vertex. Let us say what is the probability of this vertex? This is probability of this node, which is 0.6 into probability of occurrence of C, that is again 0.6. So, this is how we assign probability to a query rooted tree corresponding to a proper message set. And we can write down that leaf entropy is nothing but H of V. Note what is our V? So, V is our output of the source parser, that is V, right. And what is this denoting? What are these leaves denoting? What are these leaves denoting? This is my parse sequence A, B, C A, C B, C C. That is how I am parsing my message sequence. So, these are my VIs, right. And so, the leaf entropy will give me what is the entropy of V. So, leaf entropy, which is entropy of these leaves, is nothing but entropy of V, because this is how I am parsing my source. These are my VIs. Okay. So, this leaf entropy is given by H of V. Now, we are going to show that the uncertainty of a proper message set, which we are denoting by HY, of a query discrete memoryless source with output uncertainty U satisfies this relationship. So, uncertainty in the output of a message parser, which is V, is given by expected value of Y into uncertainty in the query discrete memoryless source output, which is denoting by U. So, again just go back and just recall what our U's and V's are. So, U is basically my input to the source parser and V is my output of a source parser. So, if you have a query discrete memoryless source, I have U1, U2, U3, UK. These are my bits emitted by a discrete memoryless source, and V is the output of my source parser. And I am using a proper message set to design my source parser. Now, please note that the branching entropy for this proper message set is given by H of U. Now, why this is true? So, again just go back and draw a proper message set. Let's draw the same proper message set that we have been working with. So, this is my root, this is corresponding to letter A, this corresponds to letter B, this corresponds to letter C. So, this is CA, this is CB, this is CC, and we consider probability of this was 0.1, 0.3, 0.6, this was 0.06, this is 0.18, this is 0.36. Right? Now, look at branching probability. Let's look at this particular node. Let's say, let's look at this particular node. Right? Let's look at this particular node at C. And if I ask you to compute branching probability, what's the branching probability? That's this probability divided by the probability of the node. uncertainty associated with that. Now note here what is this, and this probability divided by this probability divided by this. So this, if we use the notation which we have used earlier, we have used this Qij to denote these probabilities, and we have used notation Pi to denote the probability of the node. And this ratio Qij by Pi for this particular node, this ratio is nothing but 0.06 by 0.6, which is 0.1, and then 0.18 divided by 0.6 is 0.3, and this is 0.36 by 0.6, which is 0.6. So no matter what node I choose, let's choose this node. Again, this ratio of Qij by Pij, these are nothing but probability of these letters A, B, and C. So we can see clearly that branching entropy of a proper message set, basically this branching entropy is given by H of U. Okay. Now we know how the branching entropy is related to the leaf entropy. This lemma we have proved earlier, that leaf entropy is given by summation of Pi Hi, where Pi is the probability of the ith node. Now we know that leaf entropy, leaves corresponds to V, so leaf entropy is Hy. We know the branching entropy Hi is independent of I, it's always equal to H of U, so I can take that out. So what I get is then H of V is equal to H of U summation of these probabilities are the nodes, including the root node. And what is this? According to the path length lemma, the summation of Pi's is nothing but expected value of Y, right? I have from root to each of these leaves, I have my Vi's, which is the parsed message, and the length of that is Y1, Y2, Y3. The expected value of that from path length lemma is given by this quantity. So what I have shown you is the uncertainty associated with the parsed message source for a proper message set is given by this relation. It's the uncertainty in the source letter multiplied by expected value of Y, which is the length of the parsed message. Now let's try to now we have talked about the relation between the entropy of the parsed message with the uncertainty associated with the source letter. Let's just take a small diversion and let's try to compute or find out how we can do a prefix free coding of a proper message set. Now if we do a prefix free coding of a proper message set, that would then make it a variable to variable length coding. Why? Because proper message set, it takes variable length input and gives a fixed length output, and a prefix free coding takes a fixed length code and gives a variable length output. So if we do a prefix free coding of a proper message set, what we will get is a variable to variable length coding. Since we have studied prefix free coding, so I am just taking the liberty to take a small detour. So we can show that if we do a prefix free coding of a proper message set, then the ratio of average code word length to the average message length satisfies this relationship. So again, let me clarify the scheme that we are looking at. We have a discrete memoryless source which is spitting out these UIs. I am using a source parser. So I am using a proper message set, let's say, to parse my sequence. I get my VIs here. Now this is passed through a, let's say, block encoder. Block encoder, what it does is it just do one-to-one mapping of these VIs to a fixed block length code. So it maps to a fixed block length code. Now that is input to a prefix free coding. Prefix free coding. So this is this takes as an input blocks of fixed length, and what it gives out is code words of variable length, and W is the length of this output code word, which is a random variable. Okay, and Y is the source length of the parsed input sequence, and Y is also a random variable. So what I am saying is, if we do a prefix free coding of a proper message set, then expected value of the output code word length divided by expected value of the input code word length, which is basically my proper message set, which is input to this encoder, that is lower bounded by entropy. So we know for a prefix free coding, expected value of W, which is output code word length, is lower bounded by entropy of the source. The source in this case is V, so it's HV by log D, and I just now have proved that H of V is nothing but H of U expected value of Y. So if I plug this in here and divide both sides by expected value of Y, what I get is this relation. So if I do a prefix free coding of a proper message set, then expected output code word length to expected input code word length is basically lower bounded by entropy. Okay. Now let us go back to proper message set and let's talk about how can we design a proper message set that will maximize my expected value of Y. Remember, because in case of variable to block length coding, my goodness of the code is determined by how small this quantity is. So this is the output code word length, this is the input to the block encoder. Because n is fixed, I want to maximize my expected value of Y. So I would like to parse my source into sequences such that my expected value of Y is maximized. So tungsten message set is a class of proper message set which will always maximize expected value of Y. So a message set which has so many messages is a tungsten message set for a query discrete memoryless source if for the query rooted tree can be formed beginning from the extended root by Q application of the following rule: extend the most likely leaf. Now let's look at each of the points that we have mentioned here. A message set with so many messages. Now why a message set will have so many messages? If you recall, if it's a query, if U is a query random variable, then starting with the root, you will have k leaves. Let's call it U1, U2, this is UK, right? So when you start from the root, you have k leaves. Now when I extend any of these leaves, let's say I am extending this leaf corresponding to U2, then what I am doing is I am creating k new leaves. However, this was earlier a leaf, it has now become a node. So the number of leaves which is at this point is k plus k minus 1, because I am creating new k leaves, but this particular leaf, this was earlier a leaf, it has now become a node. So now my total number of leaves are k plus k minus 1. Now again, if I extend any node, I will be again creating k new leaves, but one of the leaf which was earlier a leaf is now a node. So each time I am adding, except the first time when I extend from the root, each time I am adding k minus 1 leaves. So if I try to design a proper message set, remember a proper message set will use all its leaves. So the total number of leaves I can get if I extend a node q times. So if I have so starting with an extended root, so if I have a root which has been extended, and if I now try to extend the leaves of this rooted tree, the total number of messages that I can get is given by this, which is k plus q into k minus 1, where q is the number of extensions that I have done from this extended root. Okay, I am calling this as extended root. So I have a root which has been extended to k leaves. That's what I am calling extended root. So at extended root I get k leaves, but subsequently when I try to extend any of the leaves of this extended root, I am adding only k minus 1 new leaves. So total messages which I can have in a proper message set is given by k plus q times k minus 1. Now what I am saying is this proper message set which has messages given by k plus q into k minus 1 messages is going to be a tungsten message set only if you follow this rule, that each time when you try to extend a leaf, you extend the most likely leaf. Okay, so when you try to extend a leaf, you are only going to extend the most likely leaf. If you do that, then that's a proper message set. So let us take an example. So of the ternary message set that we had, so let's say I had here, this was A, this was B, this was C, and probability of A we took as 0.1, probability of B we took at 0.3, probability of C we took as 0.6. This is a proper message set. Let's say I want to extend a leaf. Now which one should I extend? Should I extend A? Should I extend B? Or should I extend C? Now according to this, I should extend the most likely leaf. Now which is the most likely leaf? That's C, because probability of this vertex is 0.6. So I am going to extend this particular leaf. Now if I extend this particular leaf, what is this probability? A, B, C. This probability is probability of this node, which is 0.6 multiplied by probability of this letter A, which is 0.1. So this is 0.06. This is 0.6 into 0.3, it's 0.18, and this is 0.36. So now I have nodes, leaves. This has probability 0.1, this is probability 0.3, this is probability 0.06, this is probability 0.18, and this has probability of 0.36. If I extend the next leaf, which one should be? I should extend this leaf. So next I should extend this leaf. And again similarly, probability of this node is 0.36 into 0.1. So this is 0.36 into 0.1, this is 0.36 into 0.3, and this is 0.36 into 0.6. And this process continues. So if I do extension of leaves in this particular fashion, if I construct my proper message set in this fashion, then it is known as a tungsten message set. So in a tungsten message set corresponding to a Carey discrete memoryless source, if the Carey rooted tree is formed beginning from the extended root such that you extend the most likely leaf, then that's a tungsten message set. Now let us take an example of a non-tungsten message set. So let's just take the same example. So I have a message U which emits ternary alphabets A, B and C with probability 0.1, 0.3 and 0.6. Now according to the tungsten message set rule, I should be extending this particular node. But if I don't extend this node, let's say I am extended this particular node. So then this node, this is A, B, C, this probability is 0.3 into 0.1, that's 0.03, 0.3 into 0.3, 0.09 and 0.3 into 0.6, that's basically this. Now this is not a tungsten message set. Why this is not a tungsten message set? Because here I should have extended this particular node because this is probability 0.6. Instead I extended this node which has probability of 0.3. So this is not a tungsten message set, whereas this is a tungsten message set. Now you can see easily why tungsten message set maximizes expected value of y, because that's our objective. We want to parse a message in a fashion which would maximize expected value of y. Now what is expected value of y? What is y? Y is essentially the length of this parse sequence, average length of the parse sequence. So in this case you are parsing the sequences like this: A, B, C A, C B, C C A, C C B, C C C, like that you are parsing, right? So what is expected value of y? Expected value of y is nothing but, from the path length lemma, it is the sum of probabilities of all nodes including the root node, right? This is expected value of y according to path length lemma is nothing but sum of probabilities of all the nodes including the root node. Now let us take an example, the same example. Let us just take this example which is tungsten message set, and take this example which is a non-tungsten message set. Now what I did was, in both the cases I did a single extension of the extended root. In the tungsten message set I extended the node which has leaf which has 0.6 probability. In this case I extended a leaf which has 0.3 probability. Now compute expected value of y here. In this case it will be 1 plus 0.6, so it is 1.6. What is the expected value of y here? This is root has probability 1 and this node which has been just extended has probability 0.3. So this expected value of y is 0.3, whereas here it is 1.6. So clearly you can see, if I extend the most likely leaf, then that leaf becomes node, right? And the probability of node gets added to the expected value of y. So if every time I am extending the most likely node, most likely leaf, then that leaf is becoming a node and that is adding, its probability is getting added to the expected value of y. So the expected value of y will be maximum when I extend the most likely leaf, and that is why tungsten message set will maximize my expected value of y. So a proper message set of a k-array discrete memoryless source is a tungsten message set if and only if in its k-array rooted tree every node is at least as probable as its leaf. Why would every node be at least as probable as the leaf node? Because we are extending the most likely node. So if you extend most likely node, the probability of the leaves would be certainly less than probability of the node. So every node will be at least as probable as every leaf. You can just take an example here. What is the probability of the leaves here? It's 0.1, 0.3, 0.06, 0.18, 0.36. And what is the probability of the nodes? Probability of nodes is 1 and 0.6, right? You can see the leaf probabilities are less than, so the node probability is at least equal to the leaf probability is more. So you can see that. Whereas in this particular example, where we have considered a non-tungstal message set, what are the least probability? It's 0.1, 0.03, 0.09, 0.18 and 0.6, whereas the nodes have probability 1 and 0.3. So you can see here, for a non-tungstal message set, we have a leaf which has probability more than a node. But this is not going to happen if your message set is a tungstal message set, because in a tungstal message set we are extending the most likely leaf. So in case of a tungstal message set, your node is at least as probable as the leaf, every leaf. This follows from the fact that in tungstal message set we are extending the most likely, most probable leaf. It's not difficult to see then a proper message set with m messages for a discrete memoryless source will maximize the average message length expected value of y over all possible proper message set if and only if it is a tungstal message set. And I have illustrated this with the help of an example. Because we are extending the most likely leaf, that leaf now becomes a node, and the computation of expected value of the expected value of y from path length lemma, this is the summation of probabilities of all the nodes including the root node. So this particular leaf which was extended now, its probability gets added to that sum. So if we extend the most likely leaf, we are ensuring that our expected value of y is maximized. So over all possible proper message set, tungstal message set will maximize expected value of y. So if you want to do optimum variable length coding, variable to block length coding using proper message set, then you should be using tungstal message set. So now that we have described how to parse our source into proper message set, let us explain how we can use this tungstal message set to do our variable to block length coding. So we are interested in optimal block variable to block length coding. Our output code words have block length n. We have a carry discrete memoryless source which inputs these random variable u. So u1, u2, uk, that is what it is emitting. First thing that we need to do is we need to check if d raised to power n is greater than or equal to k. If it is not, we cannot find a code for that. And so remember what is n? N is the output code word length, and remember the output code word length is DRE. So how many such code words we can have? We can have d raised to power n possible code words. Now clearly this number has to be more than inputs k, otherwise we cannot map each of these inputs to a code word. So d raised to power n has to be greater than or equal to k. Now if this condition is satisfied, then first thing that we are going to do is we need to find out how many times we are going to extend the most likely node. Recall that we have said number of messages is given by k plus q times k minus 1, right? And what is the number of messages that we can encode? That's d raised to power n. So d raised to power n minus k, if we divide by k minus 1, that would give us this q. Why do we need this q? Because we need to know how many message sets to create, like what's the total number of messages that we need to create. So how many extensions of this message set, proper message set we have to do? We have to first find out, right? And how do we find out? We find this out by dividing d raised to power n minus k by k minus 1 and finding the quotient. That would give us this q. Next, we construct a tungstal message set of size m, where m is given by k plus q into k minus 1, and we start with the extended root and we will make k extensions of the most likely leaf at each step. Please recall, in case of a tungstal message set, we extend the most likely leaf, and to get a tungstal message set of size m, which is given by this, we need to do k extensions of the extended root. So at each time we are going to extend the most likely leaf, and once we have formed these messages, then we are going to assign a distinct code word to each of these messages. So let us take an example to illustrate this. So consider a binary message. So k is 2, probability of u being 0 is 0.6, so probability of u being 1 is 0.4. Now you have been asked to construct tungstal coding, and the output block size is given as 3, and output also we are considering as binary. So d is also 2, d is 2, k is 2, n given as 3. So what is the first step? We have to first check whether d raised to power n is greater than or equal to k. D is 2, n is 3, so 8 is greater than 2. So this condition holds. Next, what we need to do is we need to find the quotient when d raised to power n minus k is divided by, when it is divided by k minus 1, we need to find the quotient. So k minus 1 is 1 in this case, and d raised to power n is 8 minus 2, that is 6. 6 divided by 1, the quotient is 6. So in this case, in this example, q comes out to be 6. And of course, number of messages is d raised to power n, which is number of messages that we have is given by k plus q times k minus 1, and this is 2 plus 6, that's 8. So in this case, we can find a tungstal message set. What we need to do is we need to do 6 extensions of the extended root. So let's do that. So this is a rooted tree, and that's a root. So what I have here at this point is an extended root. The probability of 0 is 0.6, that's given by this, and probability of 1 is given by this. Now remember, I need to do 6 extensions of the most likely leaf, correct? So tell me now, so this is my extended root and I need to do 6 extensions of that. So first, what should I do? So note here 0.6 is more than 0.4. So first I should extend this node which has probability 0.6. So the first extension is something like this. This is my first extension of the node, extended root. So this probability is nothing but probability, this probability is nothing but probability of this node, this 0.6 into probability of 0. Probability of 0 is 0.6. So this is 0.36. Similarly, the probability at this particular leaf is probability of this node, which is 0.6 into probability of this letter 1, which is 0.4. So 0.6 into 0.4, that is 0.24. So after first extension, this is how my message set looks like. Now let's do the second extension. So if I do the second extension, so what do I have? I have 0.36, 0.24 and 0.4. So I am going to now extend this node, which has probability 0.4. So I am going to extend this leaf which has probability 0.4. So if I extend this leaf, now this leaf becomes a node and the extension is like this. This corresponds to letter 0, this corresponds to letter 1, and these probabilities similarly we can compute. It is 0.4 into 0.6 is 0.24 and 0.4 into 0.4 this is 0.16. So this is now the second extension of the extended root. Third, so now at this point, what are the probabilities of the leaves? This is probability 0.36, this is probability 0.24, this is probability 0.24 and this is probability 0.16. So at this point we can see that this particular node has the highest probability. So our third extension will happen from this particular leaf. So if I extend this leaf, again this probability is 0.36 into 0.6 and this probability is 0.36 into 0.4. So at the end of third extension, I have these following nodes, these following leaves. With this leaf has probability 0.216, this leaf has probability 0.144, this leaf has probability 0.24, this leaf has probability 0.24 and this leaf has probability 0.16. And I have already done three extensions done. First one was this which I showed by green, second one was this which I showed by grey color, and the third extension was the one which I showed with blue color. Okay. Let's use a different color. Let's use a light green. Now, among the leaves that are left, we can see this has probability 0.24 and this has probability 0.24, and these are the two most likely leaves. So we should be, for the fourth extension, we should be extending these leaves, any one of them. So let's extend, let's say this one. Let's extend this. So I do that, I get this, and similarly I can calculate these probabilities. This 0.24 into 0.6 and this one is 0.24 into 0.4. So at this point then, after 4 extensions, I have this node, this node, this node, this node, this node and this node. So at this point, the most likely leaf is this. So I'll extend this leaf. So if I extend this leaf, what I get here is a new leaf with probability 0.144 and a new leaf with probability 0.096. So I have done so far 5 extensions of the extended root. So at this point the leaves that I have is this, 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 this and this. And look at their probabilities. This is 0.16, 0.096, 0.144, 0.096, 0.144, 0.144, and this is 0.216. So at this point, the most likely leaf is this one. So I'll extend this. And this has probability 0.216 into 0.6, that is given by 0.1296, and this is 0.216 multiplied by 0.4, which is 0.0864. So I have done sixth extension of this extended route. So this is my proper message set. So what I have constructed is a proper message set that has m equal to 8 messages, and you can see what are those 8 messages. So one is this one, second one is this one, third one is this one, fourth one is this one, fifth one is this one, sixth, then you have seventh, and these are the 8. Okay. So then I can write out those parsed messages. So you can see, for example, this one corresponds to 0, 0, 0, 0. This corresponds to 0, 0, 0, 1. This corresponds to 0, 0, 1. This one corresponds to 0, 1, 0. This corresponds to 0, 1, 1. This one corresponds to 1, 0, 0. This one corresponds to 1, 0, 1. And this one corresponds to 1, 1. So those have been listed here: 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, and 1, 1. These are the parse messages that I am getting from my trunk style message set. Now these are my total m messages. Since I am using binary code word of length 3, so now I have to assign fixed length code to each of these messages. Okay, so I can assign any 3-bit messages. So I just did it 0, 0, 0, 1, 1, 0, 0, 1, 1. Essentially from 0, 0, 0 to 1, 1, 1, those 8 code words you can assign to any of this. Now this can be done in any order. I could have assigned this to 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You can do it any way you want it basically. Okay, this is one way, this is another way of doing it. So this is how I am doing variable to block length coding. Okay. Now let us explain the variable to block length coding theorem for a discrete memoryless source. So this ratio of expected input length by n, which is basically average message length to the block output block length of a DRE block length n encoding of a proper message set satisfies this relation. Remember, we want to make this n by expected value of y. We want this ratio to be as large as possible. So I am giving you bounds on expected value of y given n for a proper message set. So this is lower bounded by this term and upper bounded by this term, where d is the alphabet size of the block length, output code word length, u is my discrete u is basically my source letter emitted by the discrete memoryless source, P min is the minimum probability, the probability of the least likely source letter. N is my output code word length. Y is the length of the parsed sequence. So expected Y is the average input length. Okay, so let us prove this result. So probability of the least likely message in a message set is given by P times P min, where P is the probability of the node from which it stems. Now we know how, recall how we assigned probability to a k-array rooted tree. So we have a tree, k-array rooted tree. If you recall, these probabilities are defined as probability of this node multiplied by probability of these letters emitted corresponding to each of these branches. So, and what are the messages in the proper message set? The messages are nothing but these are the leaves of the proper message set. So the claim I am making is the probability of the least likely message which corresponds to a leaf in a message set is given by P times P min, where P is the probability of the node from which it stems and P min is the probability of the least likely source letter. Now since we have total m messages, right, so this probability of the least likely message must be less than equal to 1 by m. So probability of the least likely message in a proper message set is less than equal to 1 by m. Now according to Tungstell lemma, no leaf has probability more than p. Why? Because in Tungstell coding we are extending the most likely leaf we are extending. So there would not be any leaf that has more probability than the nodes, right. So then we can write, if this is the probability, this is the upper bound on probability of a message which corresponds to probability of a leaf, then from here we can write P as less than equal to 1 by P minimum. So we can write this that no leaf has probability more than P. So the P, the probability of a node, is basically less than equal to 1 by m P min. Now if we take log of this quantity and we multiply by minus and sum over all P of V. Now sum over this P of V, that's basically 1. So it would not change anything on the right hand side. We take log of this, this will be minus log of m plus log of 1 by P min, and if I multiply by minus, so minus log, this less than equal to becomes greater than equal to, and minus log m becomes log m, and this becomes minus log of 1 by P min. Then I take summation over all PV, so this will become entropy term here, and summation of PV, this will be log m, and this will be minus log of P min. So uncertainty in the leaves, basically leaf entropy is lower bounded by this quantity. Next, now what is the number of messages we have? Number of messages that we have is k plus q times k minus 1. Okay, number of messages that we have, and number of code words we have is d to the power n. So number of messages that we can have maximum is basically up to d to the power n. So m plus k minus 1 has to be greater than d raised to power n, because if that's not the case, then we could have basically done further extension of the tungstal message set. So m plus k minus 1 is greater than equal to d raised to power n, and of course our m number of messages is more than k. So from this relation I can write that 2 times m is greater than equal to d raised to power n. So m is greater than d raised to power n by 2. So m is greater than equal to d raised to power n by 2. Now I plug this one in here. So if I plug this one in here, what I get is this leaf entropy is lower bounded by this quantity. Now we have proved this result, which follows from the leaf entropy, that uncertainty in V is given by expected value of y times uncertainty in this letter u emitted by this discrete memoryless source. So if I plug this one in here, I get this relationship, right? I also know that uncertainty V is less than number of possibilities of V, which is at most can be d raised to power n. So uncertainty in V is upper bounded by log of dn. So here I get a lower bound, and from here I get a upper bound. So I put this upper bound here, and this lower bound, this I am putting it here. So combining this upper bound and lower bound, I can write that this is a relation governing expected value of y, uncertainty in u, code word length, the DRE alphabet size of the output code word length, and this is the minimum probability of the single letter emitted by the discrete memoryless source. Next I divide this expression by n times h of u, and what I get is this relation. So this will give me a lower bound on expected value of y given n, as well as then upper bound on expected value of y given s. So for a proper message set, what we have come up with is bounds on average input message length divided by the output message length. So with this we will conclude this lecture on variable to block length coding. Now in this lecture we have shown, if we use a proper message set, it has to be a tungstal message set that we should use for source parsing. Now in general, for a non-proper message set, we do not know what is the optimal way to do source parsing. So with this I will conclude this lecture. Thank you.